Assalamu alaikum dear students, welcome to our YouTube channel CD Engineering Academy. So dear students, we will discuss another exercise problem from the topic of the combined stress. The problem is 911 and the problem statement is a concrete dam has the profile shown is figure. So we have a cross section profile of the dam. If the density of the concrete is 2400 kg meter per cube and that of water is 1000 kilogram per meter cube, determine the stress on section MN if the depth of the water behind the dam is 15 meter. So dear student, the question statement is to determine the combined stresses at this section, the M and N. And we also have the height of the water. We have the dimensions of the dam. Here the length of the top is 3 meter, the length of the base is 9 meter, and the height of the dam is 20 meter. The dam is usually divided into two parts. The one is rectangle and the other is triangle. Generally the dam area or the retaining structure here which is made, the area is trapezoidal, but we have divided it into two areas for our convenience. One is rectangle and another is triangle, and behind this retaining structure, the dam is a retaining structure which retains water. Okay, so here the water also exert a pressure or a force on this dam. So here the pressure of the water is triangular load, so it also exert a resultant force on the dam. And here if we see the dam, the one part is of rectangle and other is triangle. Also these have their own self weight. So if you look into the forces, this P force of water is sliding or trying to overturn the dam, while its weight that are acting downward is trying to balance this P force and trying to balance this dam structure by friction force and to prevent it from sliding. But here we have to calculate the combined stresses at section M and N. We don't have any kind of concern with the sliding and turning, so we have to just calculate the combined stresses at the base of the section M and N. So let's discuss these forces. When we have this weight acting downward, we have these two weights acting downward, and as a result of these acts there will be a reaction force, a reactive force in the upward direction. Okay, when we look into this P force, this P force is rotating this dam. Okay, so here when this force is trying to overturn the dam, it will create a movement in the anti-clockwise direction. So here the reaction to balance this, the reaction will be in the clockwise direction. Okay, so here the clockwise direction will be produced. Usually when we look into the structure of this dam, when from this anti-clockwise movement is produced, here the toe of the dam M section, the toe of the dam, the M section, here compression will be produced. Okay, this force will cause the dam to overturn. So here at this M section there will be a compression. Okay, and whenever there is a compression, we show the arrowhead of the movement towards that part or towards that section. So that's why we have drawn the movement this way, because here at M section the compression is produced. It's a sign convention. So here the clockwise reactive movement is produced. As a result, we have also the reaction force in the horizontal direction, which will be equal to this P force. But here we are not dealing with this, because we are not concerned with sliding or frictional forces. We have just to find the normal stresses here at section M and N. For that's why we are required with the vertical force and the bending moment. So now let's come toward the solution. Here we have been given in the question the density of water and density of the concrete. So here we have to formulate an equation which relates weight with densities. Okay, so here the formula is W1 is equal to rho gh v is volume. So how this formula came, okay, we will discuss that. Let's come toward the discussion. Here the density is equal to mass per unit volume, which is known to everybody. And here hope you have studied this formula in fluid mechanics, in the properties of fluid module, where gamma is equal to weight divided by volume. This is gamma is specific weight. So when density is equal to mass per unit volume, then specific weight is equal to weight per unit volume. Okay, here the weight is equal to, here weight is a force of course, but this will be equal to mg. Put the value of mg in the weight. Here it will becomes gamma is equal to mg divided by v. Again here mass per unit volumes become density m by g. So put rho instead of this value. Okay, so gamma will be equal to rho g. Now we have to find the weight. Okay, so we have to formulate an equation that also contain the density, and from that we find the weight. So here weight will be equal to gamma multiplied by volume. So it becomes like this way: weight is equal to gamma multiplied volume. As earlier we have found the value of gamma, which is equal to rho g. So here put the value of gamma. W will be equal to rho g into v. So here the final equation of the weight. So that's why this formula came like this way. In simple way, this formula came from the just rearranging the formula of the density and the specific weight. So here W1 will be equal to rho, which is the density of the concrete dam, and then which is equal to 2400. Okay, and then g is 9.81, and volume is the, here the volume of this W1 area. Okay, W1 rectangular area. Here the volume is 3 into 20 multiplied by 1. Okay, its length is 1. The length of the dam is usually very long, so we are here assuming that we are studying the length is equal to 1 meter length. We are studying the 1 meter length area of the dam. Okay, we are finding the combined stresses for those. Okay, so here what is W1? W1 is the self weight of this rectangular area of the dam. Now come toward the W2. W2 will be also equal to rho g v2. So here rho is 2400, g is 9.81 multiplied by this volume of this rectangular area of the dam. So it becomes equal to this base, which is 6, height 20, and then half, which is the area of the rectangle. So here this is the when we equate this, we will get the weight, self weight of this rectangular part of the dam. So we have find also the W1, W2, which are equal to these values: 14, 12.6 kilonewton and W1, and 14, 12.6 kilonewton W2. So now come towards this force, finding the value of this force. So now come towards this P force. What will be the value of this P force? So here the equation is F is equal to rho g h a. How this equation came? Okay, so we know that pressure is equal to force per unit area. So here we are finding the force of the water. How much force the water is exerting on this concrete dam? So here force will be equal to pressure multiplied by area. Okay, because we have equation pressure is equal to force per unit area. So when we are finding the force, it will be equal to pressure multiplied by area. So here the pressure exerted by water on the concrete dam, here the pressure of the water is rho gh. So here instead of P we wrote this value rho GHA. The pressure of the water is equal to rho GH, and we also know that F is equal to P into A, so put this value of P here, so F will be equal to rho GHA, which is this equation. Put the value, so here to find this force exerted by water on the concrete dam, so just multiply its the density of water 9.81, height of the water which is 15 meter, and then here the area of this load. We have to find the area of this rectangular load, so it will be equal to half 15 into 1 is here, 1 is the length, this length of the base, where we are finding the combined stresses. So just equate these values, we would get 1103.6 kilonewton, this value of force. So now come towards the computation of vertical forces and bending moment, and then put those forces in the combined stress equation. We would get the compressional or tensile stresses at the section M and N. So here we will find the stresses at this M and N section just for this base of the concrete dam. Here the width of the base is 9 meter and the length of the base is 1 meter, because we are studying the area having length 1 meter, okay, not the whole length of the dam. Dam is a very long structure, okay, so we are just studying 1 meter length area in order to find the value of the stresses that are occurring at the toe, M and heel of the N part. So here we will have two kind of combined normal stresses. One will have compression stresses and the other will have flexural stresses. When we add both this type of stresses, we would get the combined stresses, okay. So actually we are combining different kind of stresses into one type of stresses. So now let's come towards the equilibrium part or equilibrium conditions. So let's consider this free body diagram. Here is a free body diagram. So we are taking the summation of F of vertical forces equal to 0. So here we have two kind of forces. Let me correct this. Here we have two kind of forces in the vertical direction, and one is the reaction. I am taking upward forces positive. So here Py, this will be Py, okay. This is not X, this will be Py. So here Py upward minus these two forces downward. Then shift both this value into other side of the equation. Add the value of W1 and W2. So we would get this answer, but I have put a negative answer with it. Why? Because these two forces, these two weights are creating a compressional reaction here, okay. The reaction Py here will be act as a compression. So dear students, also if we look at this moment here that is produced at the base of the concrete dam, so it is clockwise movement, okay. So here the clockwise movement in this direction will produce the negative bending moment acting downward, okay. It will create here the negative bending moment. If I consider this cross section area and these are my fingers rotating in the first direction, then my thumb will point the movement direction, okay, in the negative y direction. So here the bending moment produced is negative, and also the forces that are occurring at this, the reactive forces that are occurring at this base of the concrete dam are the compressive reaction, and here it will cause a compression. So that's why I have put the negative value with Py, and also I will put the negative value with the moment, because here it is negative bending moment. So here this is clockwise, I have taken anti-clockwise is positive, so this will be minus y, okay. So this will be in minus y, and then here this P force multiplied by this moment arm about this point, it is the L by 3 distance of this 15. So here 15 by 3 it will become equal to 5. So P into 5, it's creating anti-clockwise rotation, so it will become positive. And then this force of the weight multiplied by this distance. Weight is acting at the mid of this distance. So here, okay, so here the weight is acting at the mid of this length, okay, the top length, which is 3 by 2. So here this distance will become 1.5, and then this distance is the 1 by 3rd length of this base of the rectangle, which is 6 by 3. It becomes equal to 2. So here this distance is 2 and this distance is 1.5. Okay, these two distances are known, and we have to find the moment arm from this force to the midpoint where we have taken moment 0. The distance up to mid is 4.5. Just subtract the 1.5 this distance from 4.5, you would get this moment arm, which is equal to 3. So here it is at this point this force is creating a clockwise rotation, which will become equal to negative value. Okay, so this W1 multiplied by 3, here see minus W1 multiplied by 3. And how we would find this moment arm, the moment arm between W2 and this point, O point? So it will become equal to, from this side, these distances 2/3 of 6. Okay, 2 by 3 length. So 2 by 3/3 of 6 is 4, and then it means that this distance is 4, and then the distance up to midpoint is 4.5. So 4.5 minus 4, we would get this distance, which is 0.5. So this W2 is creating an anti-clockwise rotation at a moment of 0.5. So it will become plus W2 multiplied by 0.5. So here I have wrote this equation. Shift this moment into other side of the equation, and then equate this value, put the value of P, which we have find earlier in the first page, value of W1, value of W2, put here in this equation, moment equation. I have put negative sign with it because I have said to you guys earlier that this moment is negative bending moment. Okay, so equate these values, we would get the negative value of bending moment, which is 1986.5 kilonewton meter. Okay, so we have here in this section, Mn is subjected to the axial compressive force. Okay, we have a compressive force as it can be seen from the free body diagram, and we have the negative bending moment. So here to find the stresses at the section M and M, I have also shown to you guys, we have negative force and we have negative bending moment. Here the moment is negative, and here the force Py is compressive. Okay, so to find the combined stresses, just calculate the geometric properties. Here the area of this section, this is the base, the width of the base is 9 and the length is 1 meter, because we are calculating this stresses in at this length. Okay, so here the area, we have to find the area of this region, because here in this region we are calculating the combined stresses. So its area will be equal to 9 multiplied by 1, and it's the moment of inertia about y-axis. When you have to find the moment of inertia about y-axis, the cube component will be its perpendicular component. So here its perpendicular component is base, so here it will become hb cube by 12. Here h is 1 and b is base is 9, so 9 cube by 12. Calculate this, moment of inertia about y-axis will be 60.75 meter raised to the power 4. So here we have combined stress equation. This is the combined stress equation. This is compressive force, that's why it has negative value. Also put the value of my, which we have calculated here, and divide by geometric properties. Okay, multiply by z, then this will become our fiber stress equation. Simplify these values, this will become our fiber stress equation. to find the values at point M and N. So in this fiber stress equation, to find the stresses at M, just put plus 4.5. Okay, because this axis is plus z axis, so here this is plus z axis, and from this point to onward this is minus z axis, so here put the values plus 4.5. Okay, we can also say that it's to the left side of the neutral axis and this to the right side, so here it's plus 4.5 and at n section it will become minus 4.5. So if we look at these values here at section M, the stresses come out as minus 461 kilopascal, and at n section the stresses come out as minus 166.82 kilopascal. So here also remember the one thing, check the unit compatibility. Okay, I have checked the unit, you can also check the unit in the same way. So here the Newton per meter square is equal to Pascal, and this is kilo, so it will become kilopascal. Okay, so that's the main point. You can also find the check for this part, my divided by I into z. So here this m square will be cancelled out with this 4, it will come out as kilonewton per meter square, so which is equal to kilopascal. Okay, you can also write in this way. So it means that at M section the stresses are very high. Okay, the combined stresses, these were the compressive stresses, these were the compressive stresses, these were the flexible stresses, and when we add these both we will get these flexible stresses, at which M section is very high, and then the N section have the combined stresses of 166.82 kilopascal. Okay, both these are compressive combined stresses. Okay, it will create a compressive forces here. So dear student, this was our question. Hope that you would have enough idea and you have learned this question. Inshallah, we will meet in next video. That's enough for now. Thanks for watching.